So, we are discussing about the Raman spectroscopy. Raman spectroscopy. So, basically Raman effect, based on Raman effect, this spectroscopy, and this spectroscopy is very useful to study the molecular vibration and rotation. So, so we have seen the infrared, I think, yeah. So, rotational spectroscopy, or it is called also microwave spectroscopy. So, these for pure rotational motion or rotational structure of the molecules one can study using this rotational spectroscopy or microwave spectroscopy. And then we have seen this vibrational spectroscopy, or infrared spectroscopy. Okay. So, this spectroscopy used to study the pure vibration or vibration rotation of molecule, okay. Vibrational rotator or vibrational rotational motion of the molecules one can study using this infrared spectroscopy or the vibrational spectroscopy. And also we have seen that, so these can study the rotation and vibrational structure of the molecules, okay. And then third one, this electronic spectroscopy, electronic molecular spectroscopy, okay. So, here basically electronic transition, and then it is associated with the rotation and vibration of the molecules. So, one can study the rotational and molecular structure of the molecules. So, here this we are telling that rotational structure of the molecule can be studied. This we are telling vibrational or vibrational rotational structure of the molecule can be studied, right. And other one also we are telling that we can study the vibrational and rotational structure of the molecule. So, everything, all spectroscopy whatever we have discussed so far, everything is telling that this spectroscopy is used for studying the rotation and vibration of the molecules. Now, third, this fourth one, whatever I am mentioning, this also I am telling that Raman spectroscopy, it is also used for the studying the vibrational and rotational structure of the molecule. So, what is the difference? What is the difference among this all this spectroscopy, and among them this Raman spectroscopy is very popular and very useful. Why it is so? So, to understand that one has to think that one things I have mentioned, this rotational spectroscopy here, this you cannot use for all molecules like say nitrogen, oxygen. If I take these two example, so rotational structure of this molecule cannot be studied because there is no permanent dipole moment. So, this spectroscopy is not useful to study rotational structure of these molecules which do not have dipole moment, permanent dipole moment or induced dipole moment. Okay. And then also this vibrational spectroscopy or infrared spectroscopy also it cannot study this vibrational structure of these molecules because same reason it has no dipole moment. Okay. It's so both are not infrared active and microwave active molecules. So, we cannot study them using this spectroscopy, but all these molecules can be studied, their molecular and vibration, the molecular structure basically vibrational and rotational structure along with the electronic structure. So, for all these molecules, nitrogen, oxygen and other molecules, okay, can be studied using this electronic molecular spectroscopy, that because when there is electronic transition, then there will be dipole moment of these molecules, and because of that it will show the yes, it will show the rotational and vibrational effect on this electronic structure that we have discussed in details. So, core structure and this fine structure, fine rotational structure, and also and this is slightly easier and popular than this other, because here is this comes, this wavelength or wave number of the spectral lines, it comes in the range of I think visible range and ultraviolet range, okay, in that range. So, because here this it is not this spectral lines is basically it is mainly this electronic this is the electronic spectral lines. So, its wave number or wavelength or frequency, it is in the range of ultraviolet range or visible range. Now, here these lines are basically modified with the rotation, with the vibration. So, depending on this rotation and vibration, just these lines are modified. Okay. So, these lines so wavelength is or wave number is this. Now, it is slightly it is this other lines whatever we are getting is differs by the amount of this corresponding energy level separation of vibrational energy level and rotational energy level. Okay. So, here this you have basically main this electronic delta E del E, I can write del E, that is the electronic, and then your I think maybe if I write this way plus minus whatever your del E for vibration or del E for rotation, etc. So, it's just this originally this is the energy of the spectral lines. Now, this energy is slightly modified with this or modulated with this small energy of vibration or rotation. Okay. So, that is why it is in the it is in microwave range, it is in infrared range, and this is in ultraviolet range. Okay. And so So, that is why it is easier, this spectroscopy is slightly easier, slightly easier to handle, okay, because it is in visible range or ultraviolet range. Okay. So, that is the advantage of this spectroscopy. Now, Raman spectroscopy also it is in visible range or in ultraviolet range. Okay. So, in the same range. Now, then again question is, so whether these two are same or it is better. So, Raman spectroscopy is better than this one, because here also what happens that from outside we have molecules, we have these molecules. Now, this from externally incident radiation is falling on that. Okay. Now, this has some energy or wave or frequency or wave number. Okay. So, it is generally this wave number. So, this I can choose this wave number, I can choose the incident light of particular frequency, generally it is chosen in visible range or ultraviolet range. Okay. As I told, this it is easier to handle this range of frequency or wavelength. So, now this one, whatever the scattered one I am getting, so that is wavelength also or frequency also this in this range. Okay. Whatever incident radiation we are using, it is in the same range, only these are modified h nu minus h delta nu, okay, or plus minus h delta nu. Now, h delta nu, that del nu change, it's the that change is because of the rotation or vibration. Okay. So, this change is it's small, but we are observing this change in the range of this same range of this frequency or wavelength of incident light. Okay. So, still although this rotational and vibrational that energy range, that change it is in microwave range or this infrared range, but we are not detecting that that energy directly. So, basically indirectly we are probing this energy, that spectroscopy whatever we using or this wavelength or frequency we are dealing in the spectroscopy, that is actually it is in the range we have chosen, generally visible range or this ultraviolet range. Okay. So, that is why it is in the same as this one, only difference is that here you will see so many you will see it is very difficult to resolve this vibrational one. Course structure is also, it is fine, one can resolve and study and measure, but rotational one, that is very difficult to resolve and you need really very high resolution spectroscopy. So, one has to really to study the rotational effect from this spectroscopy, one has to really use very high resolution of the spectrometer, and that when you are going for higher and higher resolution, then it will pay for you have to pay higher. So, in that way, so this Raman spectrometer, so you are not dealing with that precision, okay, or you do not need to resolve that one. So, here you are dealing in this range where just it is modified with this with the effect of rotation and molecules, and that can be easily resolve and detect in this spectroscopy. Okay. So, this the advantage of this Raman spectroscopy. Now, question is this, as I discussed earlier how it was discovered, and now let us see the theory of this Raman spectroscopy or Raman effect. As I mentioned in last class that there are two lines, okay, Stokes lines and anti-Stokes lines. So, whatever the origin, there is a incident wavelength. So, this is the origin one, original original frequency of the incident one or wave number, and then you are getting lower than this and higher than this. Lower wave number means lower energy, means higher wavelength, of course. So, these are called Stokes lines and this is called anti-Stokes lines. So, it is if it is nu 0, so it is nu 0 minus del nu, you can say, and this one nu 0 plus del nu, you can say. So, these are Stokes lines, these are the anti-Stokes lines, anti-Stokes lines, and these are the Stokes lines. Okay. So, what is the origin of these Stokes lines and anti-Stokes lines? That is the theory, successful theory is there. So, so now this effect, Raman effect, it is easy to explain from quantum theory, okay. But that time it was not easy to explain, but Raman mainly, I think he used this classical concept, and that also it is interesting to discuss that one because it helps to understand physically of the system. So, let us discuss the classical theory of this Raman effect or classical theory of this Raman effect. So, you know, one has to know this what is polarizability. What is polarizability? Molecular polarizability, atomic polarizability. So, both are similar. Polarizability means if we apply electric field on molecule. So, you have molecule now, if you apply electric field E, then what will happen? This electric field, say static electric field. So, it will polarize the molecules, and because you know this in, so it is same for atom also. So, atom or molecule have this molecule, this is nothing but the multinuclear atom. Okay. So, multinuclear system. So, it has positive charge, center of positive charge, also it has center of negative charge. So, in electric field means electric field have also positive pole and negative pole. Electric field can be considered that it generates from the source where positive pole and negative poles are there. So, in between you will get the electric field. So, now you have a system where positive charge and negative charge are there. So, positive charge of the system will be attracted towards the negative pole of the electric field, and the other one, negative charge will be attracted by the positive pole of the electric field. Okay. So, that means there will be shift of the positive charge and negative charge in opposite direction. So, molecule itself is a neutral So, basically the center of positive charge and center of negative charge coincides, okay. But in electric field now this center of positive charge and center of negative charge, they are shifted in opposite direction. So, there will be induced dipole moment of the molecule, okay. So, that means when you will apply electric field, so then there will be polarization, molecule will be polarized. So, it will have the dipole moment, induced dipole moment, and if you this dipole moment, it is basically proportional to the electric field. If we apply higher and higher electric field, this separation of the positive and negative charge will be higher and higher, and this electric dipole moment, induced dipole moment will be higher and higher, because electric dipole moment, you know, this positive charge, negative charge and positive charge, okay. So, they are separated by distance r. So, QR will be the basically electric dipole moment, okay. So, this electric dipole moment, it is basically proportional to the electric field. So, when it is in molecule, so we tell this molecular dipole moment. If it is atom, atomic dipole moment, okay, or dipole moment for atom or dipole moment for molecule. Now, this dipole moment is proportional to electric field. Now, it is proportional, so there will be proportionality constant. So, this one can write equal to some proportionality constant, say alpha E. So, mu equal to alpha E. Okay. So, this alpha is basically called the polarizability. Okay. This alpha is called the polarizability, and so it's basically it depends on the molecules. It depends on the molecules, but for a particular molecules, it is constant, okay, in a static electric field. Okay. Now, for a now this polarizability for molecule, basically when these molecules are in electric field, okay. So, it is polarized. Now, it is polarized. Now, this polarizability, basically one define alpha equal to mu by E. So, that means polarizability is defined as the is nothing but the induced dipole moment for unit electric field. So, for unit electric field, what will be the induced dipole moment? So, that is the polarizability. Okay. So, polarizability. So, if you apply electric field in different direction of the molecules, okay, or molecules in electric field, if we rotate the molecules, okay. So, that means electric field is applied in different direction, and if you study the polarizability, so then if you in 3-dimensional view, if you see the polarizability, so this basically most of the cases it is seen that there is an anisotropy in polarizability. Okay. So, depending on the basically axis of rotation of the molecules and the direction of the electric field. So, this polarizability we can see if it is spherical, polarizability is spherically distributed, it is spherically distributed. So, then we tell it is isotropic, okay. But it may be also it is found that it is elliptically distributed, okay. So, then we tell it is a polarizability, ellipsoid polarizability, okay, ellipsoid, okay, ellipsoid polarizability. So, that means in this case we tell this polarizability is of the molecule is anisotropic, but if so this case, so then we tell it is isotropic. Okay. So, if it is anisotropic, so that means polarizability changes, it depends on the direction, it depends on the direction or it depends on the axis of rotation of the molecules in the electric field. So, this this dipole moment, then we can tell this dipole moment it does not depend only on this electric field, also this polarizability is not constant for a particular molecule, it depends on the direction and axis of rotation of the molecules. So, this value is not only molecule dependence, it depends on also this direction of the electric field and axis of rotation of the molecules. Okay. So, or rotation or vibration, okay, both can affect. So, this the polarizability. Now, now in case of Raman spectroscopy or Raman effect, this radiation falls on the atoms, right. Radiation falls on the atoms, not atoms, radiation falls on the molecules. Now, radiation, electromagnetic radiation, so it is nothing but it has electric component and magnetic component, right. So, then we can consider basically this molecule is getting the electric field, molecule is under electric field. Okay. So, that electric field is basically is coming from the radiation. So, radiation is there means electric, it is this molecule is in electric field. Okay. So, here whatever we discuss in terms of electric field, so basically radiation falling on it, so it is under electric field. Now, this electric field, basically if it is frequency of this one is nu 0. Okay. So, it's so we can tell that so mu equal to alpha. Now, electric field here, electric field is one can write E equal to E 0, because in this now not it is not static electric field, now it is a varying electric field. Okay. That is electric component will vary with this frequency of this radiation. So, one can write E 0 sin 2 pi nu 0 t. Okay. So, this E, it is now it is not static one, it is alternating one. Okay. So, it is alternating electric field with this frequency. Now, if you put mu equal to alpha, so just E replaced by this one. Okay. So, that means this dipole moment of the molecules will change like this, will change with the same frequency of the frequency of the incident radiation, and then what will happen? So, this dipole is oscillating then, right. Now, any oscillating dipole moment it emit radiation. So, it emit radiation, that radiation will have the same frequency of the oscillating frequency. Now, this dipole is oscillating. Why it is oscillating? That is because of this incident light, incident radiation, that is fine. So, after that with the same frequency it is radiation, it is oscillating. Now, when it will oscillate, dipole moment will oscillate with some frequency. So, it will emit radiation of the same frequency, okay, from electrodynamics, one can tell that it will emit dipole radiate and the frequency of the radiation will be the same as its frequency of its oscillation. Okay. So, it will emit radiation. Okay. So, that is the basically, so that means that is as if incident radiation falls on molecules. Now, molecules is from molecules again, that due to dipole oscillation it emits radiation, that means its radiation is coming out. So, that is we tell the scattering of the incident radiation by the molecules, and this scattering radiation whatever getting, that the same frequency as this one. So, this is nothing but the Rayleigh scattering. Okay. So, that things will happen here, it is there, and region of this is this, as I explained. Okay. And now, in addition to that, this molecule will undergo some internal motion such as rotation and vibration. Okay. And due to this rotation and vibration, what will happen? So, molecule have some internal rotation and vibration, and now external incident radiation falls on it. Okay. Now, that due to this internal motion of the molecules, okay, so that is basically due to vibration and rotation. Now, these incident molecules will be affected, okay, or it will incident radiation will affect this motion. Okay. So, that effect one has to include. So, so what will happen? So, if you consider, this external or incident radiation, it will affect the molecular motion, internal motion such as rotation and vibration, and then there will be effect on these molecules, effect on the motion of the molecules. That means it will affect the polarizability of the molecules. Okay. It will affect the polarizability of the molecules due to the incident radiation, and so that alpha we have to. So, that alpha is basically it is alpha 0 and plus rate of change of this polarizability, rate of change of the polarizability, if I write that is beta, rate of change of the polarizability. Okay. Rate of change of the polarizability, if I write beta. So, this beta, and that change will come, that change it's come. So, sin say 2 pi, sin 2 pi and sin 2 pi of so this, as I told this, it will affect the internal motion that is either vibration or rotation. So, just take any one. So, what is the motion of the vibration and the or frequency of the vibration or rotation. So, let us consider just here vibration, you can just replace with the frequency of the rotation. So, if I write nu, that is for vibration. Okay. So, then polarizability will change like this, alpha 0 plus this beta is the rate of change of the polarizability, and that is because of the internal motion of the molecules, here. If it is if we consider vibration, so what is the frequency of vibration, nu vibration, or you can just consider the rotation one also. So, now you have to replace this alpha here by this one. So, you will get basically mu equal to alpha is this one, and then you have E 0 sin 2 pi nu 0 t. Okay. So, now you know this, if you just consider here what is there as two part, one is alpha 0 E 0 sin 2 pi nu 0 t, this is one part. Another part you will have basically E 0 beta okay, and then sin A sin B, okay. Sin A sin B equal to half cos A minus B minus cos A plus B, hopefully. I think just you apply this rule, cos A minus B minus cos A plus B, half of it. So, okay. So, if you consider, so this I can put half of it, and then I will get cos A minus B, means this is there, 2 pi will be there, 2 pi will be there. So, nu 0 minus nu vibration, okay, this is one part, and then you will get minus cos A plus B. So, nu 0 plus nu vibration. Okay. So, here you are getting mu equal to this dipole moment, that is equal to it contains three frequency. One is nu 0 original one, another is nu 0 minus nu vibration, okay, or nu rotation whatever, and then another term nu 0 plus nu vibration. Okay. So, now dipole is oscillating with 3 frequency. Okay. So, this you will get now whatever scattering, incident one, now scattered light, scattered radiation we are getting, you will get this radiation of 3 wavelength. One is this original wavelength, incident one, other two is this. Okay. So, this is nothing but this one is Stokes lines we are telling, and this other one we are telling this is anti-Stokes line. Okay. So, this way, this is the following the classical theory, Raman, or one can explain this Raman effect, what is the origin of Stokes lines and anti-Stokes line. Okay. So, I will discuss in next class this quantum theory. So, let us stop here. Thank you.